Hello everybody. In the last discussion we have learned vector algebra and now it's about vector calculus. So we will start with differential calculus obviously, and before going to vector calculus we would first see how ordinary derivatives are calculated with a scalar function. So let's consider differentiation first. If we have a function f(x), then its derivative, first order derivative with respect to x, that is f prime x, is defined as limit h tends to 0 f x plus h minus f x over h. We are familiar with this definition, and this in a shorthand notation is written as df dx. Geometrically we interpret this derivative as the slope of the function. Now if we are interested in vector differential calculus, then the simplest operation would be gradient of a scalar field that becomes vector. How do we define gradient? Let's consider we have a scalar field t, and that is a function of x, y and z in three-dimensional Cartesian coordinate system. So we can write dt as del t del x dx plus del t del y dy plus del t del z dz in the form of partial derivatives. Now if we we want to take the gradient of this, then the gradient can be, so dt can be written in the form del t del x x cap plus del t del y y cap plus del t del z z cap, this quantity dotted with dx x cap plus dy y cap plus dz z cap. And we know that this right hand side is nothing but the differential line element. That means this quantity becomes the gradient of the scalar field t, that is a function of x, y and z, dotted with the line element dl. Now this gradient of t is nothing but this quantity here. So here we define gradient of t written in this way, nabla followed by t, is del t del x x cap plus del t del y y cap plus del t del z z cap. Geometrically, gradient means the direction in which the scalar field is changing. So, gradient of a scalar field is a vector quantity that has a magnitude and a direction. It's very important to note. Let's consider one example of calculating a gradient. Let's try finding the gradient of the position vector, not really vector, the magnitude of the position vector r in three-dimensional Cartesian coordinate system. As we know, the definition of gradient is this is given as del r del x x cap plus del r del y y cap plus del r del z z cap, and with the definition of r that is given here, we can clearly see that the derivative of r with respect to x will bring us half in front, and because there is x square, we will have 2x here, and it will the power of r would be minus half. That means 1 over x square plus y square plus z square, square root of this quantity x cap. Similarly, for derivative with respect to y, it will be half 2y over x square plus y square plus z square, square root of that y cap, and for z it would be half 2z over the same thing. Which is the half and 2, these things will cancel, and we will be left with x x cap plus y y cap plus z z cap over x square plus y square plus z square, square root of this quantity. So, the numerator is nothing but the r vector over the denominator, the magnitude of r. That means the gradient of the scalar magnitude of the position vector gives us the direction of r, that is unit vector along the position vector r. Let's consider another example. Let's consider a scalar field f, that's a function of all three position coordinates x, y and z, is given as x square plus y cubed plus z power 4. Now, if we calculate the gradient of this scalar field, we can write it as x cap del x plus y cap del y plus z cap del z. This is the gradient operator, and this operator is operated on the scalar field, that is x square plus y cubed plus z power 4. So, we will get x cap 2x plus y cap 3y squared plus z cap 4z cubed, which is, rearranging it properly, twice x cap plus 3y squared y cap plus 4z cubed z cap. So we can see that we have developed a del operator out of this. The way in the previous example we have written the gradient of operator was this operator was equal to x cap del x plus y cap del y plus z cap del z. Although this is a differential operator, it looks pretty much like a vector. And just because it looks like a vector, we can define its product with a scalar, its product with another vectors that would look like a dot product or a cross product. But we have to remember that it's not really a dot product and cross product of vectors, rather it is a differential operator. We have to be careful about that.